Well, we don't say.
Yes, you do. Oh, yeah.
I think we started going.
Yeah.
Thank you.
Oh, it's in good. Yeah, yeah. The first week of February, that's what I want to do. Whatever day they have, like, second class.
Okay, so today I'd like for us to finish up or just finish up with our practice problems for even and odd function on page 21. And then I'd like for us to maybe do a little bit of more practice with U substitution. And also if I can introduce particle motion for integrals. So just a little, little topics to cover. Now, I gave you a test review packet. I'm not going to start that today, but I do want to I do want to get it in your hands before the weekend, because next week there's a good chance that Monday or even Monday and Tuesday could be remote days, and if they are, then my tentative plan is that I was going to do a Teams lesson each day. So Monday, 10:30 to 11:20, and same time on Tuesday. Just going over a few pages in the test review packet. If you can join, great. If you can't, I'll have it recorded, and I'll make sure to update the website so you know how to access the video. The keys are all in the packet as well. I believe so. Let me double check. I think I put keys for each of the. Yeah, I did. Okay, so the keys are all attached in the packet, and I'll be communicating with you through Remind, the link for the Teams lesson, but then also the assignment in terms of the classwork that we're working. Let's assume that Monday and Tuesday are remote days. If they are, then I will push the date of the test back. But that also means that I also want to make sure I can keep up with the calendar. So even as I extend the days for or delay the day for the test, I may continue into the next section before the test. Okay, so the idea is that I still, I want to give you guys enough days to prepare, but then also I want to keep with the calendar, so I may be splitting time between review and covering new topic. So just to kind of give you a heads up. All right, so that's the tentative plan. We don't know exactly what next week will look like. Any questions this time? Okay. So page 21, what was the last problem that we did? Did we just, okay. Let's just see if we can work through 2 through 4. And again, I want to highlight or kind of reinforce the steps that we want to take. So the first thing we do is we always build with the shorter or the smaller interval first. So look at your bounds and choose the integral that has a shorter distance between the bounds. Build that first. And after you build that, before you look at the larger interval, look to see if it's an even or odd function, and go ahead and fill out the other side of your graph. You're going to make a exact copy. If it's even, if it's odd, you're going to make it equal but opposite. So, and then after that, you're going to focus your attention on the larger interval and see if you can build that, and also use even and odd function to fill out both sides of the y-axis. And then at the end, you're just adding up the numbers that they're asking you to, area of regions that they're asking you to add up. All right, so go ahead and try number 2, and I'll work through it the same time that you guys do. Oh, one thing I want to point out is watch out for the bounds, okay? In the sense that we want to read from left to right, especially if it just makes it more straightforward. So if something is out of order in terms of the bounds, we can always do what? Yeah, we can always flip the bounds and then just change the sign of whatever they're showing you. So that way it's more straightforward. So I think for number 2, we're okay. The bounds are in order. So the number that you see is what you're going to be able to, it'll be a straightforward interpretation. Positive 4 is above, negative 3 is below. But we'll start here, right? Smaller interval, shorter interval.
So the top number has to be the biggest.
Yeah. We would like to have the smaller number as the lower bound and the number, the larger number or the number to the right above. So we like to go from left to right. Okay, so this is how we should start out. Shorter interval, and then fill out the other side. And now turn your attention to the larger interval. And fill that out. Still an odd function, so we're going to translate that to the other side as a negative 4. So now we're just adding up what they're asking us to add up between negative 1 and 3. Okay, any questions with 2? All right, let me walk through 3 with you. So we have 2 integrals here, 2 definite integrals from 6 to 2 and from 0 to negative 6. Which one should we try to build first? 2 to 6. But something's a little bit off about these 2 here. Yeah, the bounds are out of order, which means that the 5 and negative 1 is really not as clear as, it's a little bit backwards here. So let's rewrite both of these so we have an easier way of interpreting what these numbers mean. So I'm going to flip the bounds so that the smaller number or the number to the left is below and the number to the right is above. And we can say, once we flip the bounds, this is really, it's really a negative 5. Even though it's positive 5, we read from right to left, but from left to right. This is the way that we want to be able to look at the graph. And then let's go ahead and adjust this one as well. So this is more clear now. All right, so we'll start with the shorter interval. Okay, we're back to an even function. What's next? Yeah, let's do the other side. Okay, so now we're going to turn our attention to the larger interval from negative 6 to 0, but we don't want to overlap what we've already established. Okay, so we don't want to try to change anything here, but this is more of a total. We know that after we add up these regions between negative 6 and 0, we should get numbers that add up to be 1. So if this region is already set, and we're just trying to figure out this missing region, what will this have to be if these numbers have to add up to be 1? Yeah. All right, still an even function. What can we say on this side? Now we can just add up our numbers here.
But it would be 4, right? Because it's negative 1. Those.
Yeah, the negative one was the original, which after the adjusted is really a positive one. Okay, answer is 7. All right, you guys want to try number 4. Number 4 is really the same properties as number 3. It's just instead of even, it's an odd function, but see if you can work through all the steps here. Okay, what's this missing region here between -2 and 0? -4, right? I need these two numbers to add up to be a positive 1. We're still under an odd function, so if this is -4, then this side must be positive. And only add the regions that they're asking you to be involved here. Okay, any questions with even odd functions? So, you'll see a problem like this on the test. The two biggest issues that students have with this is first is not being careful enough with the bounds and not adjusting if the bounds are out of order, and that you can obviously see that can throw everything off. So just pay attention, make sure that you're always looking at the bounds, making sure the bounds are always going from left to right. If it's not, rewrite it and change the sign of the value so that you'll be able to interpret it a little bit easier. And then the second biggest issue is not adjusting for the overlap. So understanding that the overlap is not going to overlap. It's not going to change the region that's already been established. You're just trying to figure out that missing region so that the two regions added together will add up to that overlap value. So those are the biggest issues. But other than that, if you understand the steps, if you understand to always adjust the bounds, it'll look just like this on the test. All right. Okay, let's do some use substitution practice. So let's turn back to page 19. Yeah, let's start with 3 and go through our steps. So page 19. Okay, first thing we always ask, can we just expand our way through? That square root is not going away. we're not able to separate that 4x and the -5, so we're kind of stuck inside that radical. We have to go through use substitution. Okay, so once you're convinced that you're looking at a use substitution problem, next step is find your u value. If you don't see a set of parentheses, see if you can rewrite the problem with a set of parentheses so that you have an easier time picking out that u value. Okay. We're always substituting what we've underlined and keeping everything else. No x's to have to worry about to cancel out. We can move forward, but just have to be aware we have a leftover what to include. Yeah. And once I like to have that 1/4 out in front as a reminder. Okay, this is going to be part of my final answer. If you don't do that, it's not a big deal. It's just visually, I think it's helpful to kind of organize your question this way. But if you don't do it, you won't lose any points as long as you can remember there's a 1/4 that remains into your answer. Okay, integral u to the 1/2 is ready for power rule. Again, a good indication that you're on the right track is you're looking at a simpler version of the problem you started with. All right, so start with power rule. Okay, clean up your coefficient, bring back your x variable, and then include that plus c. Okay, number 4. First thing, our first option is always expansion power rule. One thing that kind of gives it away that this can't be done with power rule is you see there's more than one term that's being added and subtracted in the radical. In the denominator. This is already going to negate the possibility of power rule. We can do power rule. There's only a single term in the denominator. Let's say it was just 5th root of x cubed. We can clean that up, bring that up to the top, and then rely on power rule. But as soon as you see multiple terms added and subtracted, there's no way that we can expand or do power rule. So use substitution is our next option. We don't see a set of parentheses, but maybe we can create one. Denominator raised to what power? Okay. Looking ahead, what's nice about this u value? Yeah, it should cancel, right? That degree 3 will turn into a degree 2, and there's a degree 2 waiting for us to pair up. So that's usually a good sign that we should be able to get all the x's to match up nicely here.
Could we make it -1/5 and brings us?
Yeah, that's good. I'm going to wait, but you're more than welcome to bring it up to the top, knowing that this has to be up top for power rule. But yeah, I'm going to wait, but if you bring it up to the top earlier, that's fine. Okay, so just like what we wanted, we want the x's to go away. Coefficient is 5/3. X's goes away, that's a good sign. We're looking at a simpler version of the problem we started with. That's a good sign. We want to do power rule, but are we ready yet? Okay, we got to bring that u up to the top. Right, so what you could do is you could bring this parentheses up to the top at the beginning and make it -1/5. I just decided to wait until the end, but yeah, some students have asked previously as well. Okay, does it matter whether you move that parentheses up earlier or wait? It's really up to you. As long as in the end you make sure that your variable is up top before power rule. Okay, keep that 5/3. Apply power rule. Add 1 to your starting exponent. Okay, flip that fraction. Okay, number 5, we can't expand this. This is inside the trig function, but we do see a set of parentheses, so we can move towards integral of cosine of u, and we should have a rule for that. So no x's to cancel out, but we do have a simpler version of the problem that we started with. Do we have a rule for integral of cosine of u? Remember, we're going backwards, right, with our derivative rules. What does cosine become? Yeah. So we're starting on this side here, integral of cosine will bring us back to sine. Okay, so take a look at number 6. We have sine and cosine involved, but they're being multiplied. So do we have a rule that looks like this that we can handle? All right, there's too much, right? We have individual rule for sine, individual rule for cosine, but if sine and cosine are being multiplied, we can't pick and choose and say, okay, I'll just do integral rule here, integral rule here. They're being multiplied, so we need to treat this like one problem, and we don't have a rule that can handle this large of a problem. Okay. So our next step is looking for our u value. Now we do see a set of parentheses around the x, but can we ever say u is equal to x? Okay, if we do that, then you're doing a one-for-one. You're basically creating the same problem with different variable. And the whole idea is that we're trying to create a simpler version of the problem. So if you just make x equals u, technically, yes, you can convert everything in terms of u, but you're just looking at the exact same problem with a different variable. And the goal is we want to create a simpler version. So can we create another set of parentheses that is better than just that x? Yeah, let's get that 10 to come out. Sorry. Get that 10 to come out of that parentheses around sine. Okay, this is a better spot for us to pick out our u value. Okay, so what could be our u value? So before we go any further, do we expect things to work out nicely here? Well, if our u value is sine, what's sine's derivative? Cosine. There's a cosine waiting for us, right? So this should work out, right? If we, whatever the u value is, it's always good to think about, okay, what is the derivative? And do I see a version of the derivative somewhere else in the problem? If I do, that's usually a good sign that we should be able to get things to work out. As soon as you build your u value, you're always following that up with derivative. Right? Cosine of x cancels out cleanly. No leftover coefficients. All we have to worry about is that u to the 10th du. Okay, page 20. Yes. The derivative is, but remember, integral. Oh, the derivative sign is the positive cosine. Yeah, derivative. Yeah, but yeah, the antiderivative would be what you said. All right, sine x over cosine of x to the fifth. There is no rules that can handle each of them as connected as they are. So we have to think about u substitution. What could be our u value? Cosine of x. Yeah, we see a set of parentheses around that cosine with that fifth degree there. So let's pick out that as our u value. Okay, cosine's derivative is negative sine. Make your substitutions. Having that negative sign x show up is a good indication that we should be able to get some things to match up and cancel out. Yeah, with the negative left over. All right, so even though the x's cancel out, we don't want to forget about the fact that there's still a negative 1 that has to be included as a coefficient in front of my problem. Okay, we clean up our integral into a simpler problem. Are we ready for power rule though? Yeah, bring that u up to the top and then we should be ready.
This one.
Mhm.
Oh, you scroll down.
Yeah,
I kept mine up. Is that correct? Still fine. I got. Yeah, great.
I just want the final answer to be with no negative exponents. So at the very end, if your answer still has negative exponents, just bring it back down.
Okay.
Yeah. Number 8, power rule. We can't do too many terms in the denominator. Denominator is too complicated here, so you have to think about your substitution. Create your set of parentheses. Identify your u value. And then move through your steps. Okay, keep track of your coefficients. Get your u variable in the right spot. And power rule. Okay, any questions? So number 9 looks more complicated. First off, we know that we don't have any single rule that can handle this much complications here. But then we would like to kind of at least have an idea, what are we trying to work towards? We have a rule that we can work towards. So let me just show you the 6 interval rules that we were able to build from our derivatives, right? Yeah, integral of sine u, integral of secant squared u, integral cosecant squared u. This is all just working backwards from our derivative rules. Do any of these look like something that we could work towards? And you. What about this one here? Is that what we're looking at?
Yeah.
Okay, so I think this is going to be the best fit. If we were to, what could be our u value then? 5 over x, right? And then if we can get u value to be 5 over x, and hope that that 4 over x squared can cancel out, then we should be able to get this to look like the rule that we want to apply. Right? Now, I do want to point something out here is that it feels a little bit strange, like how am I going to get that 5 over x to cancel out with that 4 over x squared? That x is in the denominator, and so when you go through power rule and bring it up to the top, it will produce a degree 2 in the denominator, so this will work out. Right? Because normally when we see an x, we think, oh, that just x will just become a constant, but it's in the denominator. So with power rule, everything is going to be a little bit, it's going to be a little bit different because of the negative exponent. Okay, so we're going to focus our attention then on our u value. So we're going to have 2 sets of u value because we're working towards this rule of secant u, tangent u, because we know the antiderivative is going to bring us back to secant. Okay. So if our u value is 5 over x, we would like to find the derivative, but prefer not to have to go through quotient rule. So let's bring that x up to the top and then just rely on power rule. And cross multiply. Solve for dx. To make it a little bit cleaner for me to match, I'm going to bring that x to -2 back up to the top. It's just easier to think about positive exponents. Yeah, so are you good from here to here?
Yeah.
Okay, so we're just going to do power rule. So power rule for derivatives. bring the exponent down. So bring that -1 down, which was -5, and then we subtract 1 from that exponent. -2. Okay, so now we're just replacing these two pieces with u, replacing that dx with what we have here. And then we're hoping all the remaining x's will cancel out and we can drag the coefficient in front. So we need the x's to cancel out, and they do. Okay, we do have a leftover what in front? -4/5. Okay, this fits perfectly with a rule that is available to us. Okay, integral of secant u tangent u is secant u plus c, secant u tangent u. The -4/5 will be included in our answer. And then let's bring back our x variable.
How do we go from du over -x to -2 to du x? Like, how does that x squared come back up?
So I find it easier to match and pair things up if I'm working with positive exponents. So the x to the -2 in the denominator,
Same as x.
x squared above. Yeah, I just wanted to make it so I have positive exponents to work with. Right, number 10, too complicated for expansion. We can't expand that denominator out easily. So u substitution is our next step. What's our u value? Mhm. And do we expect this to work out nicely with the numerator when we go through our derivative? Yeah, the x to the 5th is a degree that we would prefer because we know the derivative will become 5x to the 4th. That should pair up nicely with that x to the 4th. Down the road, we should get that to cancel out. Okay. Copy everything back into your next step. Just replace what you've underlined, but everything else, make sure you bring back. So bring back the 3x to the 4th, bring back the exponent 6. X to the 4th goes away, just like we were hoping. Keep track of your coefficient. And then make sure you're ready for power rule. That u variable is slightly out of place. Let's bring it up as u to the -6. So once I found my antiderivative, I'm just trying to clean up here. Coefficients out in front, that u to the -5 back down to the denominator. You don't need to separate it. You can. but just make sure you bring your u back in terms of x. I just merged it back into the same fraction, but you don't have to. And now, what about number 11? Can we rely on expansion power rule here? Okay, this one we can. You guys saw this on your quiz, right? And the reason that you could rely on power rule was because you could split this up into individual fractions, and that root x is manageable enough for us to do, right? But as soon as if it was like root x plus 1, then we got to do something else, right? But because there's a single term in the denominator, we can rely on power rule because we can split up into individual fractions, get every term separated, and then individualize each term. So whenever you see a fraction, look at the denominator. If there's only a single term like this, you can do power rule. If there's more than one term added or subtracted, you have to explore something else. Okay? So I want us to be able to recognize, even though we see a set of parentheses, we want to look at that denominator. If there's a single denominator, we should be expanding and relying on our skill from previous quiz. So let's distribute that x through, start converting that denominator into something that we can use. Okay. We know if we want to do power rule, our variable has to make its way back up. We can merge the x's together by subtracting exponents. Both terms are independent of each other. No x's divided by each other, nothing, no parentheses. Now we can do power rule. Flip that 9/2 up as 2/9. Flip the 7/2 up as 2/7. Okay, final problem here, number 12. Expand. We can't do that with multiple terms inside the radical. So u substitution is our next step. Let's get a set of parentheses to show up. Okay, we're probably going to work through pages 1 and 2 on Monday. If it's a remote day, but I'll send you a schedule on Sunday to remind, so you know what to expect.